So what we're going to do now is we're going to solve a problem for a fluid container undergoing uniform linear acceleration. And if you recall from the last segment, what we did is we came up with an equation that enabled us to determine the angle at which the free surface would be at for the condition of uniform linear acceleration. So we're going to apply that now. And the problem that we're going to look at is one whereby we have a container with fluid in it that happens to be on an incline, and there are wheels underneath the container. So we originally start with some fluid that looks like this, but then it's undergoing gravity, the effects of gravity, and so the container starts to slide down a hill or roll down a hill, and it is at some acceleration A. What we're told is that the fluid has weight W, and we're also told that the angle of this inclined plane that the container is going down is at angle phi. And the wheels, we are told, are frictionless. The gravity vector is the Earth's gravitational vector, so that's minus g times k. And the last thing, second last, our coordinate system, we have x in that direction and z in that direction, which would be the initial condition of the container, would be in that frame. And what we're told to solve for is this angle here, theta, which is the angle that the fluid, when it is moving and accelerating down this inclined plane in this container, makes with respect to the horizontal. And so what we're looking for, we want to find theta. And so that is the problem that we have. And what we're going to do, we're going to apply the relationship that we derived in the earlier segment, which I'll flip back to. It was this relationship here that enabled us to determine the angle for a container undergoing uniform linear acceleration. So let's take a look at applying that now. The first thing we're going to do, we're going to resolve the acceleration components for the container going down the incline. So let's work that out. And in doing this, we have a lot of trigonometry here. But we have our incline. It's at an angle phi. We have the gravity vector acting in the vertical direction. And if that is phi, then we know that this here is 90 minus phi. That means that this angle here on this side is 90 minus phi. And this angle here is phi. I'm going to draw a right angle here. So what we're going to do is decompose that. You know what I'm going to do? I'm going to get rid of that little phi in there because it's going to get in the way of my acceleration. Okay, so we have that, and that means that this angle here is phi. So that's applying the geometry to figure out what is going on. Now what we're trying to do, we want to decompose the acceleration. We want to know the acceleration that the container is undergoing as it goes down the surface. And for that, we know the gravity vector, we know phi, and so we can determine that directly from a trig relationship. That is g sine phi. And so that is equal to the acceleration that the cart is going down this inclined surface. We can go ahead, and what we can do is we can look at the forces. So we know sum of forces is equal to mass times acceleration. And if we express this in the plane of the inclined surface itself, we get sum of forces is equal to mass times the acceleration. The mass is weight divided by the gravitational constant, and the acceleration here is just g sine phi. The g's cancel out, and so what we are left with is the sum of forces is the weight times sine phi. So that gives us one piece of information that is not really exactly useful in terms of determining theta. So the next thing that we're going to do, we're going to break down the acceleration vector in terms of our x and z coordinates, and we're going to refer it back to what we did in the earlier segment where we were comparing to the free surface where there would be no acceleration of our container. So let's go through and do that, and then we'll apply the equation to determine the angle. So acceleration with respect to fluid at rest. And so we just saw that the acceleration was g sine phi. And if we want to decompose that into the x and the z, what we find is that we have ax and we will have an az. Now ax, and the angle of this, by the way, is phi. So we can write out that ax is equal to, it will be the adjacent over the hypotenuse, so that is cos phi, multiplied by the vector here itself, which was g sine phi. And az is going to be, it's going in the negative direction. Remember our coordinate system? Let's go back. What did we say? Z was up and x was to the right. So z is up and x is in that direction. So ax is positive. That makes sense. Az is going to be a negative, and that's opposite over the hypotenuse. So that is sine phi multiplied by the hypotenuse, which is g sine phi. Okay, so that gives us the acceleration components, and if you recall back, let me go back a couple here. This relationship here for the free surface with uniform acceleration, we're now going to use that relationship. So recall, for uniform linear acceleration, we had that the free surface could be defined in this way. Ax, so the x component of acceleration, divided by the gravity vector and scalar form, and az. So broken down into the two different components. So let's take those, and we take ax, az, and g, and we'll go through and see what we get. So plugging in the values, we have theta is equal to inverse tan, and in the numerator we have cos phi multiplied by g sine phi, and then in the denominator we have g minus sine phi times g sine phi. And what I'm going to do, I'm going to rearrange these a little bit, simplify. So we can pull the g out, and then we have a sine phi, cos phi, and that is divided by, again, I'll pull the g out, and then we have 1 minus sine squared phi. Okay, so if you remember back to your math courses, we had trig relationships. This is equal to cos squared phi, so I can rewrite it with that substitution. And here, the g's cancel out. We have a cos and a cos. So what we end up with is theta is inverse tan sine phi over cos phi, which is the tan of phi. And consequently, what we end up with is theta is equal to phi, which is kind of an odd result, but what that tells us is that the angle of the surface, if we go back to our original problem statement, if theta is equal to phi, that means that the angle of the fluid does not actually go up like we've drawn it. It actually just remains like this. So it remains parallel to the surface under uniform linear acceleration. And so that's what we get from applying the equation for the free surface to an accelerating cart that is going down an incline. So that's an example of applying the uniform linear acceleration equation to determine the shape of a free surface.